So good afternoon, and thank you very much for the invitation, and it's a great pleasure for me to present this project, which I am presenting on behalf of Haleon's data office. I'm part of the Haleon data science team. I'm principal data scientist for supply chain in Haleon, but this project has been developed by the joint efforts of a lot of people from our data office. So, the title of the project is Haleon AI Inventory Planner. And let me just give you a very quick introduction to the industrial context. So Haleon is the new name of the consumer healthcare division of GSK, GlaxoSmithKline. And after the recent emerge from GSK, Haleon has become the biggest world-leading consumer healthcare company, headquartered still in the UK. And Haleon delivers a large and extremely diverse portfolio of products, of consumer healthcare products, designed to improve people's everyday health and well-being. These include over-the-counter medicines of pain and inflammatory relief, respiratory and oral care, and allergies and a number of additional medicines, as well as minerals and vitamin supplements and so on and so forth. So really a very large and diverse portfolio of products, consumer healthcare products. Recently, there's been a lot of studies which showed a lot of evidence on the fact that guaranteeing access to consumer healthcare products has quite relevant impact on people's health and on people and on the healthcare systems in different countries. So, for example, this study published by the Consumer Healthcare Product Association, value of over-the-counter medicines to the US healthcare, states, for example, that each dollar spent on consumer healthcare actually alleviates the pressure on the healthcare system by at least 7 times. So it's quite relevant that I would like to point that this is not just a commercial problem. This is not just a commercial project. Guaranteeing the service levels and the accessibility, the access to a lot of people to consumer healthcare goods has proven to have impact on everyday's health. In order to do that, Haleon relies on a very complex global multi-echelon supply chain. We start with purchasing raw materials, then we manufacture those goods in a number of factories. We also get some help from contract manufacturers, and then these goods are shipped across the world on a logistics leg, and then they get on local distribution centers, and then down to a number of different distribution channels. And this is extremely complex, and as you can imagine, every efficiency gain in this multi-echelon complex supply chain is a very big impact, both commercially, but also in terms of guaranteeing service levels. So, challenges and opportunities. Optimal inventory management is a really classic problem, but in the last 3 years, a few things happened. Like, for example, we saw unprecedented demand patterns for certain products. Can you make an educated guess what happened with all the paracetamol-based products at the beginning of the pandemic and other things? So we also experienced delays and disruptions in global supply channels. And in addition to that, there's been some people absent from factories because of COVID reasons and quarantines and other things like that. So there's been really challenging period. In addition to that, many industries, and Haleon is part of that group, has stated really ambitious and really increasingly relevant sustainability objectives. So every gain in terms of efficiency and resilience of complex supply chains becomes very important. And every product or every tool that helps that it has relevant practical impact. So these are the challenges, but there are also really interesting opportunities. So, for example, digital visibility in industrial processes determines unprecedented opportunities for optimal orchestration of global supply chains and other complex industrial and engineering systems. This level of digital visibility on processes and shipments and everything else wasn't there just a few years before. So it's very relevant taking advantage of that, and it's very relevant that there are enormous opportunities in starting leveraging that in terms of really doing modeling, really using that for optimization purposes and optimal orchestration purposes. In addition to that, our human understanding of the customers and and the understanding of the customers and expectation and appreciation of our products have increased enormously in recent years. So these are interesting opportunities for actually applying advanced modeling and applying really non-trivial techniques. In this context, Halion's data science team is supporting the supply chain digitization program, and that supply chain digitization program enables optimization initiatives with industrial but also with academic partners in all these different areas, like, for example, smart control systems, smart maintenance strategies, optimal operational scheduling, predictive or proactive risk management, logistics and distribution optimization, multi-echelon supply chain optimization. So these are all areas in which we are working very, very actively. In this context, we decided to focus on an extremely important segment of our supply chain where the digital visibility collected from different systems was extremely promising to give high impact and high results. And this segment of our supply chain includes part of manufacturing. So we have visibility on certain manufacturing processes, part of manufacturing, is it working? Part of manufacturing, international logistics, and then distribution centers located in different markets, plus some downstream distribution channels in the cases where the inventory, the decision-making on inventory is still can be agreed. The decision-making on inventory is still to a certain extent, under our control. In order to solve this problem or optimize inventory policies, we have created this highly integrated ensemble of state-of-the-art components designed for our specific industrial reality. And it contains the following components. First of all, we have demand forecasting model, which works on portfolio of products. We have a supply forecasting or delivery forecasting model, which uses upstream visibility, digital visibility on processes to tell when the purchase orders which have been already placed are expected to arrive. Then we have the actual probabilistic inventory management model, which leverages the information provided by the above two components. And then we have implemented all that in an actual tool, which is able to provide recommendations or suggest optimal actions to planners. So let me start with the first of these components, the demand forecasting component. So first of all, the demand forecasting component is used for two purposes. One is obviously long-term planning. Long-term planning includes also manufacturing, allocating resources, and scheduling then the manufacturing operations. And in order to do that, we use the long-term forecast over a certain time horizon, about between 18 and 24 months. Based on that plan, the supplying plants and the distribution centers, different markets, have to they have the so-called service level agreement. And there are strict rules in that service level agreement of what are and how orders can be placed, both ordinary orders and both, and let's call them emergency or expedited orders in certain cases. And then the weekly review of the inventory in every distribution center is obviously used as the short-term inventory, the same forecast over a shorter time horizon, which is the time horizon affecting the specific inventory management decision. So with this project, we actually moved from consensus-based forecast, which was used in different markets, actually agreeing between the markets and the supplying plants what are going to be the expected demand patterns, to, let's say, mathematical machine learning forecasting algorithms. And to be honest, the consensus-based forecasting wasn't bad. The performance in terms of accuracy, so we managed to win against the consensus-based forecast eventually. But the real reason why we're trying to compute and to use alternative methods is to be able to use them in this picture. And in order to have a forecasting method that can be used in that context, we had to actually build a probabilistic distributional forecast and not just a point forecast, because all the decisions and all the computations computed by the rest of the construction needed that. So the very first version of the model, after some research and some experiments and what might work against the let's say judicial forecast. The first implementation of the tool included univariate method, which was based on light GBM model. Then we did a lot of experiments in actually including multivariate forecasting because we're expecting the benefits of multivariate portfolio forecasting in the case of like hot starts of new products and other things like that. So for example, we experimented in this direction. So far, we haven't seen enormous advantages in doing that, but by increasing the portfolio of products, perhaps in the future that would be an interesting opportunity. We started, as I said, with certain model, but actually, so this is the distribution of demand forecast, which we actually needed for the purposes of doing the rest of the computation. And we did that, by following best practices in resampling and bootstrapping of the residuals, but having very neat distribution in these cases, and then translating them in a distribution forecast for the future was extremely important. As I mentioned, we made some experiments with actually multivariate portfolio forecasting. Those were not terribly impactful, but inspired by the results of the M5 competition, we implemented as a next step in the development of the process in this framework of continuous development and continuous improvement. We created and actually we implemented some global methods able to provide additional forecasting, or alternative forecasting sources. So what we see here is actually something that was very well explained in this paper from the M5 competition. Then when we have global forecasting methods, the cross-learning between different time series becomes quite relevant and becomes quite substantially impactful for the quality of the forecast. What you can see here is what happens if we gradually increase the portfolio of products, and this is the univariate forecast from our standard method, and these are the two global methods which perform in a slightly different way. But what you can see is that especially when we reach certain number of elements in this portfolio for the purposes of the pilot specifically, the performance, the error decreases substantially. So in line with theoretical expectations. And then we started, actually implementing certain metrics which are able to actually measure and assess the quality of the distribution of forecasts. But this is work in progress. Continuous development, as I mentioned. The second important component of our model is the delivery forecasting model. So in absence of real-time tracking, we don't have real-time tracking, we detect the completion of key milestones of the purchase order from the moment that the purchase order is placed to the moment when the purchase order arrives at the distribution center. And again, this covers a relevant chunk of the supply chain, which is part of different echelons. So it's not really a multi-echelon problem, but covers elements of different echelons of the supply chain. So we're tracking both manufacturing and logistic milestones. And we apply this method, survival analysis-based process completion method, inspired by an international conference of process mining in 2021. And survival analysis based on so we estimate the completion of the delivery time, progressively estimate the delivery of the purchase order based on the completion of certain milestones. And in this case, survival analysis means that we apply both fitting and regression techniques in order to have a viable distribution which tells which fits the time to delivery, the time to delivery intervals. And this has been very successful. So we dynamically compute and we tell the model what are the expected completion time for every purchase order. So this is an example. You can see certain milestones being completed, and then the expectation ranges, the confidence ranges of our forecast getting gradually more and more precise. Same thing here. We are detecting a delay. We are detecting a delay in the shipment. Again, continuous development in this area allows, for example, better techniques to compute or use deep learning methods to actually do the regression part of the scale and shape parameter of the same variable distribution. And there are a number of alternative techniques which we are experimenting and trying in the context of this continuous development of the tool. Obviously, adding closer real-time visibility and routing information to the regressors, for example, would be we expect this to be extremely impactful, and other time completion forecasting algorithms. Then we have the inventory model. And the inventory model has been developed in collaboration. We had this short and very productive consultancy contract with the Management School of Lancaster University. And they suggested that for this specific purpose, what we have to do is to use an order up to level model combined, in which we allow allow placing an emergency order if we see the danger of a stock out. So the inventory model is order up to level, periodic review, and possibility to place an expedited order if necessary. So in this context, when you order up to level, obviously you have to compute what is going to be the demand. So what is going to be the demand, and we did that computation quite accurately. And the point is that we have short review period, but we have long lead times. So in that situation, we really had to, do the math and then sample properly in line with best practices in order to be able to cover different demand patterns with the probabilistic distribution, with the probabilistic forecasting that I just mentioned. Similar situation with how we compute the expedited order trigger. The expedited order trigger, especially when you have long lead time and short review period, needs to take into account the fact that there might be multiple orders traveling in the same time. And we did all the maths and basically had this model which basically creates the trigger for the expedited order probabilistically in this sense. So there's no time, but I'm very happy to tell that we actually then had a formal model which computes the service level as a function of the sensitivity of the trigger and the safety stock levels, and the curves were qualitatively like this. And this is like a small homework which I would suggest, if you try to work out with these ingredients what is actually the formal model that computes the service level. It's very interesting. So in addition to that, another component was the scenario simulation engine. We generated a demand forecast and then implement a complex product-specific set of operational constraints, such as minimum order quantities, incremental order quantities, and so on and so forth. Supply the available information, then generate supply patterns from the distributions, and then evolve the scenario by including the actual demand data and compute the resulting KPIs in each case. So these are the results. We first of all started with a kind of grid search, but then, so for example, on these pictures, you can see exactly as we expected qualitatively the shape of the ISO service level curves. The contour plot shows the inventory levels, and these curves here show the number of expected emergency orders that you can place. So in this case, you basically do a constrained optimization going like this, and you can choose either to have a more aggressive or less aggressive inventory strategy based on how many expected delivery emergency orders you can place. And here is a slightly more, cleverer way of searching the space in order to build those, to build gradually those, curves, ISO service level curves. And now I wanted to show you how the actual model works, and the model works like that. Here you can see how the inventory evolves. Here you can see what are the orders that it places, the demand forecast, the supply pipeline, and then here you can see the sensitivity of the stock out trigger. So when the screen changes, you will see actually how the model shadows the current process, the current planner using the current process. and this is how it goes. So in this specific case, we requested, a service level of 99% with a conservative strategy, and we got to a reduction of the inventory by comparing here and here by 12%. But then actually the planners are allowed to choose different service levels, for example 98%, and see what happens, and have recommendations compatible with those. And this is what happens. So realize 16%, is that 16? Yeah. Of service level at 98%. But then the planners might decide to push the service levels to the almost impossible 99.5%. And the result that we still managed to realize about 10% reduction in the total inventory. And then we have aggressive strategies and so on and so forth. I would like really to point this point here. We call it the inventory plan, and this is genuine. What I mean by that? So product after product after product, we saw these reductions. And product after product after product, the model proposed different strategies. The model proposed different strategies. So here, for example, you can see a very similar demand pattern to what the planner was doing. Here you can see a less frequent and completely different demand pattern with respect to what the planner was doing. And here you can see a completely different demand pattern with respect to the previous examples and respect to so in these highly constrained set of constraints and situations, the model proposed different strategies and displayed some sort of non-trivial behavior in showing that. Very last comments. We made comparisons in order to understand, is there more sense in investing in better visibility, or there's more sense in investing in better demand forecasting algorithms? And this is itself a very relevant business question. And we show that actually increasing the upstream visibility and having better, forecasts of what's going when exactly the orders that we have already placed are going to arrive, is actually more beneficial. So here we compare different scenarios of perfect demand knowledge and perfect forecast knowledge, and then the combination of the two. This doesn't exist only on paper. This exists actually, we have implemented the tool, and this is just a small demo of that. The tool exists. Here are the recommendations for the planners, and here you can choose different service level. The tool adapts itself. We have the long-term projection. If you point just your cursor and anywhere in the page, you can see all the information that you need about what are the inventory levels, what are the orders, when they're expected to arrive, and the tool computes some sort of long-term projection of all the inventories and some sort of ideal pattern for orders in the future. Time to wrap up, please. Yes. As a very, very conclusion, I would like to point out to the judges how this project is aligned with the criteria for the competition. So first of all, the level of demonstrable benefit. The solution guarantees the requested service level, so we definitely observe that. And the solution guarantees the requested service level much more efficiently than the current processes, and not just the current processes, but the tooling that support the current processes does. The intellectual and novel content of the solution. It's a highly integrated ensemble of state-of-the-art models, which I haven't seen elsewhere. And I personally have reviewed many proposals for inventory management models from different vendors coming to us to show us, fantastic AI applications. And I can testify that this is quite successful and quite original. Recommendation to optimal inventory policy and execution of every single order. The likely longevity of the solution. First of all, this is a project which is aligned with the strong digitization program of the global Halion supply chain. So there is a huge investment in digital tools, and this is aligned. And in this context, we are certain that it's going to be to enjoy longevity. And especially, I would like to point out continuous development framework, which I kind of illustrated quickly. The excellence of OR process, state-of-the-art algorithms, best practices in everything we did in terms of scientific rigor. Even the design of the pilot. The design of the pilot has been extremely rigorous. But most of all, deep understanding. So in industrial context, you are tempted to rush. In industrial context, stakeholders want to see results. Very often you hear challenges like, well, AutoML can do that. No, AutoML cannot do that. So actually doing the maths, understanding deeply everything that we are doing and properly, with the proper scientific rigor, because trusted science is one of our pillars, is something that I would like to point as part of the excellence of the OR process. Thank you very much for your attention, and I'm very happy to answer any questions.
Okay, over to the judges for their questions.
Hello. Thanks for that. Can you clarify for us, has this been implemented within the company?
So this has been implemented in terms of tooling. It has been prepared. Currently, it's under piloting in a limited number of places. So it's not yet implemented. So it's not adopted everywhere. It has been implemented, but it's like on an adoption curve.
Okay. And are there plans to adopt it?
Yes. Yes. As I mentioned,
what are those plans? When will it be fully adopted in the company?
This is a difficult question to answer. As I mentioned, currently we are in the process of implementing certain set of platforms that are supporting the digitization, in terms of digitization of the global supply chain. So in parallel, we are piloting the tool in order to, so our solution, and then the plan is that as soon as that process will be completed, we'll be integrating both solutions. But they are dependencies. They are dependencies which are both technological and business dependencies. So we are, very much happy that to happen as soon as possible, but it's not going to be obsolete because of our continuous development framework. So even if we're piloting it in different places and gradually move into global adoption, it's not going to be old in the meantime.
Okay, thank you. And just one more question from me before I pass the mic to my colleagues. You talk about state-of-the-art algorithms there. Could you very, very briefly give us some evidence for why they are state of the art?
Yes.
Are there comparison with other algorithms? And what is it that makes these algorithms particularly impressive?
Well, I mentioned the global forecasting methods. The global forecasting methods. So we were really inspired by the results of the last M5 competition. So we studied the papers and we implemented what they were suggesting. And actually, as I mentioned, we saw the benefits of implementing global methods with the increase of with increasing the number of time series included and the benefits of cross learning, which were claimed in the papers. So this is just an example of something that we picked something and tested in practice and actually checked the theory. If really those benefits claimed in the paper, we can observe them. And this is just an example of the fact that very, very recent. And also the process mining paper that I mentioned before. It's really recent. So in order to avoid obsolescence of our tools, we are in this.
Okay.
This is our approach.
Thank you.
Thank you very much for your presentation. In terms of the benefits, you highlight 12 to 15% reduction in total inventory. What is the financial impact of that?
It's very big. I cannot, but I cannot tell you figures. We have assessed that, and we have made a number of also financial scenario simulation, and that required an additional level of complexity because people start asking you at which point you are invoicing, right? So, but we have done that, and we have the figures. I'm for commercial reasons not allowed to show, but to share those. But as you can imagine, it's a global company with massive inventories all over the world. So it's like really impactful in terms of economic benefits if we're able to optimize those.
Okay, and then the other question I have is moving away from point-based forecasting to probability-based. How do the end users action this? Because if you need to communicate to with your suppliers, are you working within a range? Because if you go over, it's waste. If under, you may not be able to satisfy your customers. Yeah.
So our customers, which are the planners, they have specified certain business requirements for us. So first of all, the tool should be able to provide recommendations for optimal orders compatibly with a selected service.
So is that a point-based value or is it a range?
For the end users, it's just a recommendation. Place an order of 10,000 items. And this is what they see. They participate, if you wish, in the discussion on are they inclined to use a more aggressive strategy that allows a high number of emergency orders, or they would like to have a more conservative strategy. But this is the discussion. So then we tune the strategy. But from that point on, what the end users, the planners see, it's a real recommendation. Today, on Monday this week, this is your weekly review, we recommend you to place an emergency order of this amount of items and an ordinary order of this amount of items. And in let's say in pilot circumstances, they can accept that recommendation, or they can not accept that recommendation, and they can leave a comment why, and then we'll be updating the strategy and working on that. So basically. The end result is very, very simple and user friendly for the tool is user friendly for the planners.
Okay, and then last one from me, consensus-based forecasting to ML. How did you get the end users on board?
This is still on the journey of convincing. Because it's been many years in which consensus-based forecast has been used, and it's actually, as I said, good quality. But yeah, the discussions are around introducing in the future additional predictors and additional aggressors based on local knowledge, based on, for example, information on specific things that are impacting demand, such as promotions and other things like that. So this is the way in which we are moving the forecasting discussion forward. But yeah, we kind of needed that probabilistic aspect, which the consensus-based forecast currently is not offering. So,
thank you very much.
Thank you.
Quick one, Ruth, please. Sorry.
Thank you very much. Just coming back to this, the implementation path. How have you been working with the potential users?
Yes,
so far.
Since the very beginning of the project, we have collected business requirements. We have they collaborated enormously, for example, in understanding. I mentioned a complex set of constraints. I mean, the local planners were extremely helpful in explaining in what kind of constraints the service level agreement translates. So yeah, we have collected continuously requirements and collaborated.
So they've fed into it. What have they fed back to you about, say, the end user interface that you've shown us? Have they accepted that and said, yes, we're ready to?
That was developed in a completely agile way on like continuous review and continuous feedback and continuous interaction on that. So what you saw on the screen completely reflects their requirements.
So in that interface, you've got the potential for users to override your recommendation and to feedback on the overriding. How are you planning to use that information? At
the conclusion of the pilot, we'll analyze basically. So that was actually part of the experimental design of the pilot, making sure that we are able to collect all the feedback and making sure to track then back what was the impact of not accepting certain decision, and was that beneficial, and what happened afterwards. So actually conserving all that information and conserving all that information contextually has been planned exactly for those purposes, and understanding what went wrong, and should we change strategy, should we adapt it to more conservative or this kind of evidence.
Thanks very much.
Thank you.
Right. Need to move on. Thank you very much.
Thank you very much. Thank you.
Cool. Hi, everybody. So my name is Dom, and today I'm going to talk to you about order fulfillment at Gusto. So first, a little bit about myself. So I'm a senior data scientist at Gusto. Been there for about 2.5 years. Previously working at McLaren Applied Technologies and British Airways, also doing OR data science type stuff. And I hold an MSc from Lancaster University in OR. And I'm actually wearing the same shirt that I am in that picture, so that's nice. So Gusto is possibly not quite as famous as GSK, so I'll explain a bit about who we are. So we're a recipe box company. So every week we send our customers between 2 and 5 recipes out of a menu of about 80, which changes week on week. And we like to think of ourselves as a data company that loves food. And fittingly with that, we have a large data team which kind of impacts all areas of the business. And just to give you a couple examples of some of these, we have kind of automated menu planning where we optimize the different business objectives. So this is kind of like how do we change the menu week on week to either save costs or kind of up our customer satisfaction, give us operational resilience and stuff like that. We have forecasting, so we have a suite of forecasting algorithms that help us basically plan our network of our supply chain and do it as efficiently as possible with as little waste as possible. We have some more customer-facing ones, so churn prediction, when we think people might stop buying our service, personalized reckoning recommendations, and of course, order fulfillment, which is what I'm here to talk to you about today. So I'll give you a bit of context about what we do. So in our factories, we have either one or multiple picking lines. You can see my great little diagram there. And so basically, these are a central conveyor which boxes move down, and they can come off onto a number of picking stations. So this is normally between about 40 to 150, depending on the size of the line. And a box can come off onto these stations and pick up a subset of its SKUs from that station. And so a SKU is a stock keeping unit, and in our example, it's just an ingredient, so a potato or a tin of beans or something like that. And so the box can come off into the station, get picked into by an operative using a pick by light system, then wait to go back into the line and continue on to get whatever other SKUs it needs from different stations. So that's a bit how it's kind of set up, and this provides us with two different problems. So firstly, given our set of SKUs and our set of stations with all the spaces that they have to put on items, where do we want to put them? And that's our first problem. And then once we know where we put them, when we route orders down them, how do we route them in the best possible way? And so what we really need to know first is what we're actually trying to achieve. And while there are various considerations that I'm not going to go through in detail here, the main thing that we want to do is maximize our line throughput. So this is the number of boxes that we can finish per hour going down the line. And this is very important for us because we have kind of capacity that we need to reach. And if we don't do so, we might miss our outloads and not be able to deliver boxes to a customer. And that's obviously an outcome we really want to avoid. So a bit more kind of context about the problem, which will make our approach a bit more understandable. So firstly, all of our orders will be composed of different recipes. So there's a kind of structure there to what SKUs are in it. It's not just arbitrary. Some recipes are a lot more popular than others. So if you kind of put it up on the graph in terms of popularity, it will look a little bit like the kind of power law curve you see there, where some are much more popular than other ones. We have a lot more space for the SKUs on the line than we have unique SKUs. So each station might have between 40 and 70 slots for different SKUs on them. And as I said, we might have 40 to 150 stations. And we might have 400 odd SKUs. So we have a lot more space. And so there will be some SKUs that we want to put on the line more than once if they're particularly popular. And the last thing is that we've done research in the past to understand what helps us maximize our throughput. And there are really two things that we want to do. So firstly, we want each box to go to as few stations as possible. And this kind of makes sense because you can imagine when a box is getting picked into, that's kind of like value add time. But the time it spends waiting to get into a station, waiting to get out, maybe recirculating on the line because the station it's going to is too busy, that's all kind of dead time. So we want to avoid it to up our throughput. But we also want to kind of distribute the work as much as possible because you could have every box going to just one station, but if it's all the same station, then it's just going to be a massive bottleneck and all the other ones are going to be idle. So with that in mind, I'm going to kind of explain some of the intuitions behind our first algorithm, which we call PFO. And so PFO is our pick face optimization algorithm, where a pick face is basically like the setup of the line. And there's kind of two intuitions that we use. So the first is that if the recipes are grouped together, like on a station on the line, then an order only has to go to at least one station maximum to pick up that particular recipe. And if two of the recipes it needs are on that station, it can pick up two, and this helps us with our station visits. And the other thing as well, which is quite important, is that the more popular a recipe is, the more likely you want to have it on the line. So the more times you want it on the line. And again, this gives us more options for to pick up the more popular recipes and allows us to kind of spread our workload across all the stations. So I'm going to explain how we actually generate a solution for this. So this gives a solution, basically says these SKUs will be on these stations. And so how it works is that we group all our SKUs into recipes. So this is just a collection of the SKUs that are in a particular recipe that we have. And we initialize them all with a priority, which is a very low number. So in this example, we've got 1 divided by 10 to the 10. And I'll explain the relevance of this a little bit later. But with this, we then initialize a priority queue data structure. which is basically a kind of queue data structure where every item in it has a priority. And you can use a get command to pull the next item from the queue. And the item that you pull is the one which has the lowest priority, which is slightly counterintuitive because you might expect it to be the highest, but anyway, it's the lowest, which one you get. And so once we've initialized our priority queue, we basically run until our stations are full, and at each iteration, we pull out the next recipe with the lowest priority, and we put it on a random station by adding all the SKUs in that onto the station. And then once we've done that, we have to update the priority for that SKU group that we've just placed. And we update it by adding 1 divided by the popularity of that SKU group from our forecast. And so the reason we do this is that it basically ensures that the priority of any SKU group is the number of times it's been in the line divided by the popularity of it. And obviously the numerator, the number of times it's been in the line, makes the number bigger and kind of pushes it further back in the queue, which is what we want the more times it's been down. But then the popularity, the denominator, makes the number smaller and brings it to the front in the queue. And by doing this, we kind of balance our thing of wanting to have recipes grouped in a station, but also have the more popular ones down more times. So that's a kind of explanation of how we generate solutions. And you might really be thinking, how do we actually evaluate them? Like, how do we know that the solutions are any good? And the best way to do this is to explain our second order fulfillment algorithm, OR. So I'm going to explain our order routing. So it operates on a single order at a time, but generally will optimize a batch of orders at once. And so how it works is, for the first order, we initialize all of our stations with a workload cost of 1, and we solve a weighted set cover problem for that order, which basically says, get the lowest cost stations I can go to pick up all the SKUs that I need. And once we do this, we have a set of stations that we can go to, and then we have to decide which ones that we pick up those SKUs from. And so if of the stations that we've picked, an item we need is only on 1 station, then that's fine, the decision's made for us. If it's one that is on multiple stations, as might be the case of a popular item, we normally go to the lowest cost station to pick it up, trying to distribute the workload as we said. And so now we've got a kind of mapping for a particular order of saying we're going to pick up these SKUs at these stations. And then what we do is we go through and we update the workload costs of the stations that we visited. And so the more picks that we've done there, the higher our workload cost. And then this is moved on to the next order to optimize, and it uses the workload cost that we've kind of built up over time. So as an example, with our first order, you can see all the costs are 1 because we've not done any routing yet, so it's essentially an unweighted set cover problem. We go to 3 stations, pick up the most stuff from the second one, and then you can see that we carry on these costs to the next one. And by doing this, we kind of can build up a workload profile over time. And the reason we use a weighted set cover problem is it kind of balances our goals of minimizing the number of stations that are box visits, while also trying to distribute our workload as much as possible. And so, as you can imagine, our kind of key metrics of this are over a whole batch of orders, what are the average station visits we've got for a box, and we also use what is the standard deviation of that workload that we calculate across all the stations, across all the orders. And these are the kind of 2 measures we know are important for our throughput. So, as you can't imagine, OR is directly dependent on PFO. It needs to obviously know what SKUs are on what stations before it can route them. So it's actually a great way to evaluate the outcome of PFO and decide what ones we want to pick. So to explain what you're seeing here, the 2 charts you can see are what we call OR graphs. And so on the x-axis, they've got the different stations on a line. And on the y-axis, you've got your red line, and that's the number of boxes that visit each station. And you've got the blue line, which is the number of picks that happen at each station. And you can see that the top one doesn't look very good. Part of it has got some very spiky workload, and the bottom one is very flat. And this one is particularly bad because this is for one of our legacy lines, which has half the stations having 40 spaces for different SKUs and half of them having 16 spaces for different SKUs, which is purely like that for legacy kind of space, like physical space reasons of the factory, but makes it quite tricky to find a good solution. And so we found that using this way of basically, and using the randomness inherent in the priority queue, we can create a number of solutions. So normally between 100 and 1,000, depending on the difficulty of the problem for that line. And then we can run OR over them and then to look at our throughput metrics and use these to pick the best solution. And as you can see, especially for a line like this, there's quite a big difference in terms of how the workload is distributed depending on which solution you pick. So why does this work? There's a couple things that go for us. So OR is a kind of decomposed greedy algorithm. So we route each order one by one and then carry over the information from all the previous routings to make them kind of work at a reasonably optimized level on a batch. And that means that it's really fast to run. We can order 1,000 orders in about, 2 or 3 seconds, something like that. And this means that it's a reasonable thing that we can use to evaluate different solutions. And the other thing that helps us is that our solution generation process for PFO is itself quite good already. It relies on a lot of intuition and knowledge we have about the problem. So most of the solutions it gives us are quite good. And generally, if you have 100 or 1,000 or a not too big solution set, you're going to come across some great solutions in there from which we can pick the best one. I'm going to just mention a couple other design choices that we've made as well. As I said, the decomposition of OR makes it quite quick. It also makes it very scalable because you can imagine, because each order is done one by one, if you double the amount of orders, you just double the amount of runtime. We did, it could have been done potentially as a kind of global optimization where we route all the orders at once, but sometimes we have over 10,000 orders to route. It could end up being in kind of hundreds of thousands or millions of variables, and it isn't really practical to do in the amount of time that we have to do this, since it's an operational algorithm which is running all the time. And because of that, we found that our decomposition works quite well and gives us the speed that we need from it. And secondly, OR, it's still not the fastest evaluation for PFO. There could probably be quicker ways to do it, but we've actually had quite a lot of trouble finding a good objective function that we can correlate well enough with throughput to optimize directly against. And we found that using OR as a kind of simulation for it is a really good way to get good solutions. Although I should mention that we are currently doing some research into are there any kind of, decent enough proxies that we can use, because you can imagine if you had a really quick evaluation on a solution that could cut out, 75% of the worst ones, then you can explore 4 times as much with not much extra time cost, and then only run OR on the best ones. So that's a bit about the algorithm, and then about how it's actually impacted our business. So the recipe box market is growing, and it's quite competitive. And for us, this is the order fulfillment is really a big source of competitive advantage. So there is actually an ability for our warehouse management system to do some naive order routing. And having looked at what it would have done, we do it in about a quarter of the station visits, which is a huge improvement and creates massive improvement in our throughput. And at Gusto as a company, in the last few years, we've kind of gone to new sites, we've increased our capacity, expanded our menu, expanded our proposition, and none of this would really have been particularly feasible without having this working for us. And it's something that's been in operation for several years. So we've been optimizing our order fulfillment for, I think, 5 or 6 years now. This current generation of algorithms, which I just explained, has been going for a bit over 2 years. In this time, we've made little improvements. We continue to make improvements. As we release new sites, we need to kind of update them for the new sites, etc. But we kind of envisage that we'll continue working with them and improving them for years to come. And so that is all from me. One thing I should mention, this is not all my work. This is the work of lots of other people at Gusto over quite a long period of time, although I have been heavily involved. But yeah, that's it. And please give me any questions.
Over to the judges.
Can you quantify the financial benefit to the company?
It's quite tricky to do, but off the top of my head, when we moved from this generation of algorithms to the previous generation of algorithms, we lost about, as in we managed to do everything with about a station visit less, and some analysis that we'd done previously showing that would basically improve the throughput by about 80 boxes per hour. And you imagine that capacity, 80 boxes an hour over 100 hours of production a week is 8,000 a week across, I think, 4 or 5 different lines. So this potentially is 30-odd thousand boxes additionally of capacity that we have a week. And given that they sell for between 25 and 50 quid, and we sell them every single week, the capacity gains that you've got are in the orders of millions. Obviously, you have to sell all that demand for it to work, but that's the kind of increase in capacity that we can see, and that's just going from the kind of previous generation to the generation that we have now. Before we had this, we basically couldn't scale in the same way that we have been able to, because as I said, the number of station visits you might get might be like 16 or something, which was just unfeasible for scaling, whereas now we do it in a quarter of that amount. So that's a bit of like back of the envelope maths, but I think that gives the scale of what it does for us.
Thank you. And your last bullet point there, you talk about being set to be used for the future and improved. Can you say a little bit more about what the improvements could be? What are your plans for improvement?
Yeah, so we've mentioned so far basically throughput as our main kind of objective we want to optimize for. And I did actually leave out that there is a couple other things that we consider. So one is about where we place stuff on the line. So with a subset of our ingredients, for example, we say we're going to put really fragile stuff at the beginning of the line, at the end of the line, and really like stuff which it can crush, like tins or whatever, at the front. And this is because obviously we don't want to, put in a load of peppers and put a load of tins on top of it because it's just going to crush it. So we do this for a subset of SKUs at the moment, but we want to kind of expand that out and do it for more things because it impacts one of our other key objectives, OTIF, which is basically on time in full, and so part of that is quality. So that's kind of one of the things that we want to look at in general. Another thing is that because this works by putting down recipes one at a time, there is a limit where you get to a certain size of number of recipes that it will just not run. And so there might be a way to basically generate solutions that doesn't rely on the current way, but that is still good in terms of throughput, which will help when we want to scale our menu to 200, 500, however many recipes we might want to scale it to. So those are kind of two of the main ones, but there are other potential optimization objectives that we might want to think of as well.
Thank you.
Thanks very much. This is another world. Are there any people in the world? You showed a fulfillment line which had no people involved. Is there any need for human intervention? And the reason I'm asking that is for the follow-on question, which is, if there is occasionally need for human intervention, do the algorithms make a difference to how much?
Okay, so I may have not made this clear. So there are people who are in the stations picking and putting the items into the box, simply because obviously it's quite hard to get a robot to pick up a pepper and put it into a box in a good way. So there are humans involved. But in terms of the output of the algorithms, apart from people deciding to kind of like change the config that they might want for a particular week, it's kind of all automatic in terms of how it works. But yeah, so it's mostly automatic in terms of the actual algorithmic output we get every week.
Thanks. And just coming back to the question of the value to the company, you can only make money from the boxes that you sell.
Yeah.
So at what point does improving the capacity of the lines actually make a difference to the company bottom line?
It's a very interesting question, and it really, it kind of depends on conditions that are wider than just the company. Obviously, as you can imagine, we made massive capacity growth during the pandemic because this is a very attractive proposition when you're stuck in your house. So at that time, this kind of thing was incredibly valuable. It's probably a little bit less now, given that we're not in the greatest economic situation. So it really depends on where we are as a company. But I think that would be basically the goal of if we can develop this further to be able to have more than one objective, you can kind of decide, do we actually need this extra throughput, or can we concentrate a bit more on maybe putting stuff on the line in a better order, which makes us have less damages, for example. So I think where we want to get to is where, based on what we actually need that week, we can decide what's most important to us in terms of optimization objectives, if that makes sense.
Thanks, Gavin. How do you balance between increase in volume versus your SLAs? Yeah. Because you're optimizing for throughput, yeah?
Sorry, so do you mean in terms of like how long it takes us to run?
So let's say that more customer demand comes your way. How do you balance that versus getting things out to them?
Again, it's probably done outside of these algorithms. Like if more for like demand is coming into the business, then this is something that we kind of address by well, I mean, at a longer term, like building new factories to be able to do it, because there's only so much you can squeeze out of any one factory. I mean, these, in terms of like the run times of this, they're both pretty quick, if that's what you're asking to run. Sorry, I don't think I fully understand your question.
Not so much. Yeah, runtime, that is a planning phase, isn't it? And then, you execute. So let's say that, because you're optimizing to minimize, time that you get things through, you have more demand coming through. You have SLAs that your customers are expecting you to meet. How do you work within that? You are constrained by the number of stations you have and so on and so forth.
I guess based off what we know about how these run and what we can kind of expect of throughput, this is managed by people who manage our capacity at a kind of network level, and they'll basically set a demand from a particular factory which they know is feasible, and that's kind of how that's managed. And as I said, the algorithm which is running all the time, or like very often, which is the actual order routing, is really fast, so that's never really a bottleneck on the company at all. It can, route a large set of orders in less than a minute. So for us, that's not really much of a constraint. But in terms of how we manage that, it's more done at a kind of like network-wide level. And people will say to the people working in the factory that we need this much, these many orders done, and they'll know whether that's feasible or not, given basically their experience.
Okay, one last question. If we were to do this again, what would you do differently?
What do differently? It's a good question. One thing, I don't know if it's necessarily differently, but one thing I think we could have done is done more research in how we generate those solutions for how we set up the picking lines. So the current solution works pretty well, but I think we found one that worked well and then went with it because we had other stuff to do, whereas there are potentially other ways to come up with a solution which don't have some of the drawbacks like we have now. So a big one being, like, as I said, because you put down recipes together as they're grouped, when you hit a certain menu size, the algorithm doesn't work. It's something we're working through now, how to deal with that, and it'd be one of those things where it'd be nice to have put a bit more time and research in up front to look at different methods for generating solutions. And however they are generated, we are still able to kind of evaluate them using the same framework.
Okay, great. Thanks very much.
Cool, thank you.
Excellent. So thank you so much for coming to listen to my talk. And it's an honor to be here and to be invited to give this presentation. So thank you very much. So today I'm going to talk about a clearance price optimization problem for Tesco, which is the company I work for. So my name is Ramon. I work as a lead data scientist within the data science team at Tesco Technology. So yeah, let's kick off. So what I'm going to go through today is I'm going to introduce the problem of what we call markdowns, which is clearance price optimization at Tesco. I want to talk to you about the challenges of the problem and how we approach those challenges, talk about the impact and some conclusions and some nice spillovers of this solution as well. So first off, why does any retailer do markdowns? So markdowns are price reductions that are applied to a product when the product is coming towards the end of its life. So this is something that retailers everywhere in the world throughout history have done. The goal of markdowns is, it has multiple goals, but largely it's done to maximize revenue. So once you don't want that product in your shelf, you want to get rid of it, but while squeezing out as much money as you can. At the same time, you want to minimize waste, so you want to minimize the amount of products that you have to end up not selling. Depends on the product. If it's something perishable, you really want to avoid that going to waste. And there's other things that you might want to optimize, like if you're a large retailer like us, like optimizing for display time, so making sure that a product's making best use of the space available in store for the right time. So For anyone not familiar with the problem of markdowns, this is really what it looks like. So this is taken straight off the textbook, one of the nicest textbooks, I think, on revenue management by Bob Phillips. If you are a retailer selling, I don't know, garden chairs, and you want to get rid of your garden chairs within the next 20 weeks, you might do something like this. You might observe demand looking like this. That's your base demand, so that's how many units you might sell every single week at your list price or base price. Then you apply a 30% reduction, and you see a bump in demand, which leads to a bump in sales. That bump will slowly decay. Customers will get used to it. You'll expose less customers to that reduction. So you want to sell more, so you put another reduction. Now you put a 50% off, so you observe another bump in demand, same thing happens, and then you really want to kill that product, so you put it down to 70% off, at which point you're recovering very little revenue from these last few markdowns, but they're necessary because you want to get rid of this product. So this is what we call a price ladder, which is what merchandisers at Tesco have been trying to decide on for many, many years before the data science team came along and helped them with this problem. So the key question for markdowns is what should this price ladder look like for any given product category or like product? So I'm just going to quickly run you through the areas in Tesco where we use markdowns. So we use them within food and non-food types of products. Within food, we have fresh foods. So these are fresh foods, like strawberries. Packaged foods, so these are, I can't describe it better, packaged food, things like chocolate or candy. Then we have non-food. So non-foods are things, well, primarily clothing and home. So we have a clothing brand called F&F, and we also sell, well, I've branded it home here, but within Tesco we call this general merchandising. So this will be anything from pans, pots, duvets, things like that you might use at home. So within these, we have another category that's important for us, which is things that are seasonal versus things that are non-seasonal. We tend to think of most fresh foods as non-seasonal for now, so I haven't categorized it there, but this is an important category for us. So this is where Tesco uses markdowns right now. Now, this is the solutions that I'm going to talk about so far have been implemented here. And this was a poor choice of color, I now realize. But what I want to highlight is that we have now got a solution for automated markdowns that is currently live and operational within non-seasonal clothing and home, all of fresh foods. And in trial right now, we have a heavy focus on doing the same thing for seasonal products. It's a bit of a harder problem, but we have for seasonal packaged products and seasonal home products, particularly, we have active trials. So in a little bit more detail, how does this problem look like? So if you are, again, you are a merchandiser selling garden chairs, when you look at say we are optimizing the reduction that we want to apply to a product, and for argument's sake, say all we care about is revenue. So from this, it's really easy to know that at 0% reduction, you will make some revenue based on your base demand, and at 100% reduction, you're going to make no money. You're going to give everything away for free. Based on the demand, particularly how that demand changes with price, we can infer a curve that looks like this, at which this is just a toy problem. You could see that if you wanted to maximize revenue, you should apply a markdown at around 65% in this particular case. Now, the optimal solution to reducing waste will be always to, well, now let's introduce waste. If we wanted to minimize waste instead of just maximizing revenue, the obvious solution is, well, just give everything away for free because things will fly off the shelf. But then we'll make no money. Usually for us, there's an optimal balance somewhere. The best solution typically lies at a reduction that balances these two objectives. The majority of, we spend a lot of our time trying to come up with, what is the right objective for a particular problem. Now, I actually don't know what this little figure is. My colleague introduced it. I think it's an iceberg, but it also might be a man with a bandana and a hat. But anyway, my point is that the problem's not that simple because we're not only optimizing for a single stage. As I showed in the first example, markdowns are usually applied in stages. So we have a price ladder. So we have to optimize for multiple stages. And I showed you many different product categories. Each of these also has many different timescales associated with them. So we also have to do this across different timescales. And not to mention that we have to do this at massive scale. We have thousands of stores with thousands of products. So that's a lot of decisions to make. So let me run you through roughly what these timescales and what are the considerations on some of the key product categories. So for home and clothing, we optimize for clearances happen in clearance campaigns. So merchandisers get together, decide on a range of, 500 products that they want to mark down because they want to get rid of. And we decide on the appropriate markdown price based on things like our forecasted sales, the time of the year, particularly if things are seasonal, the current stock in store, and other supply chain considerations, like how much stock is in the depot, have the merchandisers bought additional stock, and that kind of thing. So for home and clothing, the solution spans, the timescales of this is in the order of many weeks. So for clothing, these markdown campaigns usually last about a month, and we have usually 2 stages. So that price ladder has 2 steps. For home items, that can last anywhere between 3 to 4 months, usually with 4 different stages as well. And for this type of problem, the solution is highly driven by space in store and product range changes. So just to give you a quick idea of the scale of this problem, this involves about just over 600 stores, large stores in the UK, with 35,000 decisions a year that we need to do. Quickly having a look at fresh food timescales. So fresh food timescales, we have similar types of considerations. So we optimize based on forecasted sales, current stock, and so on. But the timescales are much faster. This is a much more continuous problem. So usually, our colleagues in store will go and perform 3 to 4 scans on items throughout the day. And at each scan, we have to tell them what price, what reduction, if any, should they apply to strawberries. So this is highly driven by stock availability and expiry date. And because it's daily, the scale of the problem is much bigger. And also because fresh food sells in all stores. So this puts us around 500,000 decisions a day. So that's a lot of automated markdown decisions to make. So I just want to run you quickly through some of the modeling challenges that we have. So modeling demand is, it's actually quite hard. We have a lot of data, as you can imagine, but that data is never really in the right places. And what I mean by that is we started this type of automated solution about 4 to 6 years ago. But prior to that, either there was very little historical data for reductions, or the reductions that had been applied to products were just not that creative. You know, things like merchandisers just applying a 50% discount for the last 10 years. So that means that while we might have a lot of data in this region at 0% reduction, data on different reductions, particularly very high reductions, is actually really hard to come by. So that's what I mean by that. There's a lot of effects of seasonality, and for a lot of products, this is actually a really hard cold start problem. If this is a new product, we might have nothing to go base our models on. So, you know, estimating demand as a function of price change is quite hard. And it's also a highly uncertain problem. So some of the optimization challenges that we face, one of them is scale. Just the sheer amount of decisions that we have to make is one of them. And the second one is uncertainty, at least from my point of view, because we are optimizing over estimates that are fundamentally very uncertain, as I've shown in the previous slide. So I just want to give you a quick sense of how we approach this problem. So we pretty much view this as a Markov decision process, where you have a state which you make a decision based on a policy. That decision leads to an action. From that action, you collect a reward, and that leads to the next state, and so on. So that's your basic Markov decision process. For us, this Markov decision process looks like this. Our state is normally, it's a vector that's a lot more complicated than this, but usually it involves previous sales, previous stock. On that state, we then apply two key models. One is a base demand. So if we applied no price action, what would be our state in the next time step? So this is one predictive model. And the second predictive model is, if we apply the price action, how would that affect the state? So this is what we call a demand uplift model. So this is how we view the problem. So this actually kind of breaks down the problem nicely for us into a prediction and an optimization problem. So this is our prediction problem. It effectively boils down to modeling this relationship as best as we can. And as I talked about, this is an inherently hard problem. The types of approaches we use, we don't have one approach to the problem. Rather, we've built a collection of, we've built a toolbox of different solutions that we apply in different contexts. Because as you'd appreciate, we have a lot of different types of products, product categories, business constraints, and so on. So the key thing is we treat this as a predict-optimize problem with different tools within this. Because of the fundamental uncertainty on the prediction, we put a lot of emphasis and a lot of focus on probabilistic modeling. On the optimizer side, I mean, this I don't want to sound like a buzzword bingo, but we really do apply all these type of algorithms in different contexts as they're appropriate. Just to talk a little bit about the types of systems that we have. So largely for fresh and packaged foods, we have a fully automated system that effectively pushes prices straight to the PDAs of our in-store colleagues. Whereas for clothing and home, this is a human-in-the-loop decision support system. So this means that our system doesn't automatically push prices to stores, but rather provides price recommendations to an army of merchandisers that then review these recommendations and take action on the back of them. Our philosophy is very much to deliver, always on end-to-end solutions that integrate into Tesco's infrastructure. I'm going to whiz through the design pattern that we have because of time, but I did want to talk a little bit about how we automate this. And the recipe is actually quite simple. If you look at it in a high level, we have data sources that involve mostly product sales, stocks, and prices that we aggregate in a step we call ETL. We then have a model training pipeline that runs on a schedule that can be weekly, daily, monthly, depending on the problem. That trained model dumps a little file. That training process dumps a file with a trained model that can then be used by our optimization routine, whichever one this is. That optimization routine is responsible for generating scenarios. So what store, product, combination am I going to optimize for? What's my current state? That kind of thing. Then we optimize. Once we optimize, we then push these prices through an API to the different systems that are downstream. So this usually involves price labeling and price execution, I forgot here, so that when a customer pays in the till, the price is reflected. For human-in-the-loop decision-making systems, UI, and also dashboards. So I'm going to skip through the tech stack that we use, but we leverage a very rich tech stack. And I'm going to quickly talk about the impact. So before I talk about this, I just want to point out that we have a very experimentally minded team. So we're very experimentally minded. So we like doing trials to validate our solutions. And these trials involve effectively splitting into test and control stores, applying different reduction strategies for a period of time, and evaluating our metrics. And the way we work is, this is very embedded into the way we work. So we define a business problem, model, work on a model, produce a proof of concept, perform a trial, and iterate. This loop is never ending, but this is our working philosophy. So I'm going to quickly just go through some highly sanitized figures of impact into the business. I'll first talk about our fresh food trial. So fresh food trial started in 2019. When we were in the first iterations of the system, we did about three or four trials where we played around with different waste penalties. We actually played with different optimizers. And one of the things that we found is that we could very, very quickly drive revenue up at the expense of waste. So we could make a lot of money whilst wasting a lot of food. The solution that we ended up putting in stores that has now been live for about a year, since last summer. I can't tell you exactly how much revenue it makes, unfortunately, but it has an impact on the range of a few percent, which is big for Tesco. What I can tell you is that our solution actually increases revenue whilst minimizing waste. So we have focused on a waste penalty on our objective to ensure that we are driving waste down in the range of 3 to 7%. A little bit about impact on recent trials. So we recently ran a fun trial on Easter eggs during Easter. And I mean, again, headline figure is we showed that we can make more money than the merchandisers, which apply very, very simple markdown strategies. But we do this on a store-by-store basis. So that means we can actually make a lot more money than them. And in this case, we actually had no significant change to sell-through, which measures waste. An interesting case has been our clothing and the general merchandising solution. This has actually been live for over 4 years. But we focused on the wrong thing initially because we deployed it, we gave it to the merchandisers, and they were using the tool for about 2.5 years. And we actually had no idea what the impact was on the business because we hadn't conducted a trial. So we shifted our mindset about 2 years ago to trials and actually started measuring the impact of this solution. So recently, in 2022, we've been able to conduct trials, and again, I can tell you that revenue has gone up for both cases. In the same range as fresh food, it's a few percent improvement, which is big for the business. There are some really nice positive spillovers that I want to really quickly talk about. So, which I personally really like. One of them is that we currently have, so Tesco has a food donations scheme where charity partners get notified of food that's going to go to waste at the end of the day. And currently, Tesco has a team of software developers that have developed a solution that sends a message out to charity partners towards the end of the day saying, hey, come to this store, there's going to be this much left of these type of foods. That solution it's very nice, but it overestimates a lot of the donations. And one of the things that we've been able to do is for them to take advantage of our demand model to effectively give our charity partners a much better idea of the actual levels of food that would have gone to waste that's available at each store. So that's a really nice positive spillover. And I can see that you're looking at me telling me to shut up. So I can let you read the conclusions, but in conclusion, we've developed this system that's fully automated. The solution has been live for home and clothing. Recently has gone live for fresh food across all stores. Our impact is very clear and measurable, and we have adopted a mindset of being able to measure things and conduct trials. And not to mention that this has some additional positive spillovers for our communities. And yeah, thank you.
Thank you very much. In one of your earlier slides, you talked about the methodologies that you used, and you mentioned meta-heuristics and simulated annealing.
Yeah.
Could you give us some indication of the level of analysis that you did to pick the right algorithms? Why simulated annealing? Why not taboo search or something else? And would, could you just give us some indication of that analysis, please?
So I can't find the right slide, so there's two levels, really. One is offline benchmarking. So we care about, we have a brute force solution that we always compare against. So whatever solver we use, we compare it against a really crude brute force. So that's something we do offline. During the early days when we were developing that, there was a simulated annealer basically competing with a simple dynamic program. And our metrics were really how latency, because this was specifically for fresh food. We cared a lot about latency just because of the scale of the problem. So our analysis was simply comparing different strategies in terms of how quickly they can get to the right solution or approximately to the right solution compared to the brute force solution. So this is before going to trial. Once we are happy with this, and in this case, we really weren't, like our meta-heuristics were on par with other approaches like dynamic programming, we actually put it on trial because here you're optimizing over a prediction, and it's really hard to know which answer is right because it's just a prediction. So the ultimate test is to put it on trial. So we put it on trial. That's how we decide ultimately, with practical considerations as well. Mm-hmm. So we particularly like meta-heuristics because you can get to a reasonably good solution without finishing all the steps. Without too many iterations, and you get the measurable benefit in the trial. So they work quite well. I'm a fan. Yeah.
Okay, and thanks. And to what extent do other problems impact upon your problem? So I don't know very much about supermarkets other than that I use them, but I do know that where you place products within a store can affect how well it sells. And one could imagine that your revenue, which is one of your objectives, could go up if they're placed in a different place. Does that problem impact upon your problem?
Yeah. I mean, there is a lot of things we can't measure. So we're fortunate that Tesco's quite systematic about what it does with stores. So a lot of the spacing decisions are actually homogeneous across stores. So that's nice. Mm. What's a challenge for us is when things go wrong. When a store goes and does something else for its own operations, or when stock counting, for example, it's quite hard. When stock counting is not done right, then we get the wrong data and we make the wrong decision. There's many variables, but we are lucky that a lot of these variables are controlled and are the same across stores on a normal basis. The problems with the exceptions and when things don't go according to plan. I don't know if that kind of answers the question, but
Yeah, it does. Thank you very much. Thanks.
Thank you very much, Edmund. Do you take local regional context in your modeling?
That's an interesting question. Yes, and not in all models. In some models, yes. In some models, we don't. I don't know if you remember, but fresh foods, this is done store by store. For the rest, it's not currently done store by store. It's done at national. So this is a distinction. So I guess the answer is it's complicated. In some cases where we find it's relevant, yes. In the model, it's hard. In the optimization, definitely, when the optimization is done at store level.
Thanks. And then the other question is, for your clothing, you're currently focusing on seasonal stuff, yep. And you also mentioned that waste isn't, just trying to read what I wrote down, waste isn't a KPI. So why do you need those seasonal, why do you have to look at those non-seasonal models for clothing?
What was the question, sorry? Why?
So waste isn't part of your KPI.
In clothing, the reason it's not, it's because most things will get cleared to zero in the end. So nothing will get wasted.
That's correct.
Yeah.
But you have, or you plan to, I think you are trialing the non-seasonal aspect. My question is, why that path, if nothing is going to go to waste? Because you can sell on, I believe what you do is, you sell on after the season or whatever it is, yeah? So why do you need a seasonal, a non-seasonal, a model for the seasonal bit, yeah?
So actually, let me explain a little bit more. Let me see if I can find this tree. So with clothing, seasonality is, I would say not as critical because of the timescales. The seasons are things like summer. It's a very broad season. If the product hasn't sold, once we've cleared as much as we can, it's possible to just give it another week and see if it sells more. So for clothing, it's one thing. For home products, this is perhaps a lot more transient because these are very, very specific seasons that have really sharp demand peaks. So the demand peak will look like this and then fall off a cliff. So at that point, you really want to make sure you capture that and you have enough products to sell at your peak and you actually sell all of them because the demand will fall off a cliff. And you can't move Halloween by a week. So for those very, very specific seasons, actually, the note I made is incorrect. Waste is much more of a factor because we want to make sure that once demand falls off a cliff, we have sold through over 99% of things. That's how we formulate it. We want to make sure that once demand falls off, things are sold.
Okay. Then last one for me, what was the most challenging aspect of the work for you?
It actually comes back to your question, which is, how do you decide between algorithms and between solvers? Because you're faced with, even when you have the ability to put something on trial, which is something that's really nice to have, but when you do put something on trial, you're risking a lot. And deciding what exactly will you put on trial, and then what will go live and be implemented across all stores. That's the hard part, especially when you have a lot of competing ideas from a team of really smart people, all of which want their solution in. Having a process for making these decisions in the most structured, reasoned, and systematic way. I think that's the most challenging thing.
Thanks very much. I just have one question, I think, since time's getting on. You described on the fresh food side, you described the possibility of having increasing profits, but at the expense of your waste measures. And then you said that what you've got is something that increases profit by a certain amount, and also reduces waste. Who decides on that balance? Because presumably you could reduce waste further at the expense of the level of profit. So it's who decides on that, and how frequently do you revisit that balancing?
The second part of the question is a lot easier to answer. It's revisited a few times a year. As and when, it's a few times a year, around, I would say, 2 to 3. So it's every few months, that's decided. The decision process is really not straightforward. So before we took on this solution, this was part of the supply chain team. So the supply chain team had their own solution for this, particularly for fresh food. And I mean, they had a process for deciding on waste penalties, but they tried to make a healthy balance, between how much is it acceptable to waste versus the need to make money. That's a reality. I'm not sure how much more I can say on that, but the decision involves many areas of the business. It's not just down to us. I mean, what we're good at is at optimizing for things. On that point, one of the interesting things I have been trying to pursue is the idea that these food donations bit that I talked about at last. Currently, this has been a really nice spin-off that has happened this summer, and it's not really integrated into our optimization routines right now. So these are two separate systems, and although our food donations can now leverage the fact that they can leverage our demand model, I would like to pursue thinking about how we link these two things, because food that goes to waste and doesn't go to charities, that's the real problem. And I'd like to integrate these two things so they work together. But I don't know if I've managed to answer your question or not. But
given our time limits, that's fine. Thank you.
Okay, folks, thanks very much for your time listening to this. I know we've got a hand for a question in the audience. Perhaps you'll follow up on break. We really must finish it there. So if we could thank all three presenters. Due to my admin failure, we failed to get out the voting form, so the audience voting, we're going to give that a miss this year, I'm afraid. Sorry for that. As I mentioned earlier, the three judges are now going to get their heads together and agree which of the three will be our winner, and that will be announced at tonight's gala dinner. So we look forward to that result later. Thank you, folks.